Okay, so last time we finished up chapter 4, um, and we're off now to chapter 6. Again, we're not going to do chapter 5, which is nuclear chemistry, so we're skipping that chapter completely, so we won't do it. So we're off to 6. This should be, again, chapter 2, exam 2 material here we're starting. So we're going to talk about chemical bonding in this chapter. We're also going to talk about nomenclature, which is naming things, and let's go talking, I suppose. There. So we're actually going to start with nomenclature, I think. And nomenclature is just a fancy word for how you name everything. And we're going to talk about different ways to name different types of compounds. And there's really sort of two types of compounds that we're going to talk about with bonding, and also two types of compounds really that we're going to talk about with naming. And that is, for example, we have an ionic compound. And when we have an ionic compound, that is always a metal and a non-metal coming together. So the deal with that is we talked about those periodic trends the other day. And based on those periodic trends, not metals are pretty much the ones that have all those trends that they want to give away their electrons. And non-metals have pretty much all the opposite trends of they would like to keep their electrons and take other people's electrons. So when these two guys get together, we do get a transfer of electrons that occurs. And the result of that is we actually make ions. So we make a cation from the metal, which is a positively charged ion. We make a anion from the nonmetal, which is a negatively charged ion. And in an ionic compound and an ionic bond, there's absolutely no sharing of electrons happening. It is what is referred to as the electrostatic attraction, also a fancy word for opposites attract, basically. So the positive ion and negative ion are attracted to each other, and that is really what holds an ionic compound together through an ionic bond, is that sort of mutual attraction of the positive charge and the negative charge. Once again, important to remember, especially when we talk about bonding as well, that there is no sharing of electrons there in that type of compound. And that is different than a second type of sort of bonding and compound, which is sometimes referred to as a covalent bond, a covalent compound, or a molecular compound, sometimes referred to. And the difference here is also kind of what's involved. And this is typically two nonmetals together. So two nonmetals coming together. And it really does also go back to our periodic trends we were talking about. All the nonmetals, if you look on the periodic table, are essentially all sitting in the same spot, which means that they all have really the same sort of periodic trends. They all basically want to hang on to their electrons. They all want to basically take other people's electrons. So when these two nonmetals come together, the best that they could sort of agree upon is we will not give away our electrons, but we will be okay sharing our electrons. So in a covalent bond between two nonmetals, that is where we get sharing of electrons that occur. As we'll talk about a little later on in this chapter, it could be equal sharing of those electrons, or it can be unequal sharing of those electrons. But the sort of hallmark of a covalent bond is some type of sharing is basically happening. And much like in an ionic bond where the positive and negative attraction with no sharing of electrons are happening, that keeps it together. That sharing of electrons is pretty much what keeps that bond together between the two atoms. Now, depending on whether it is an ionic compound or a molecular compound that has covalent bonds, in terms of the naming aspect of it, we do name them differently depending on sort of what's going on and what type of compound that it is. So we'll get into the naming part here first, but just a wonderful drawn periodic table. There are certain elements that when they do make a charge, they do have sort of fixed charges. And when we look at the periodic table, everybody in group 1 pretty much will have a +1 charge. Everybody in group 2 will pretty much have a +2 charge. We kind of skip over there the transition metal region and go to kind of group 3 where boron is. They will have a +3 charge, but really who we're talking about here is pretty much aluminum. That's pretty much who we're talking about there in group 3. Group 4, we really don't worry too much about, because this is sort of where the staircase is kind of coming down. Group 5, group 6, group 7. And when we're talking about 5, 6, and 7, we're actually talking about nonmetals. So these again are the ones that are above the staircase. So we're talking about everybody, in this case, above the staircase. Group 5 typically will make a -3 charge. Group 6 a -2 charge, and group 7 a -1 charge there. So it's kind of like a 1, 2, 3 skip, 3, 2, 1 going backwards. And again, we're talking about nonmetals here with the negative charges. As we talked about, that is who basically makes a negative charge, are nonmetals. Because also below the staircase, you have some metals basically hanging out there on the periodic table. So again, above the staircase there as well. The transition metals, which are here in the middle, for the most part, the transition metals have the ability to make a variable type of positive charge. Because they're metals, they will lose electrons. They will make a positive charge, but they can make a variable type positive charge, like copper can be +1 or +2, depending on the situation. Iron can be like +2, +3, also depending on the situation. So they typically don't have fixed charges. With that being said, there is actually, though, 3 exceptions to that are transition metals and do have fixed charges. And that is, I'll just write it here, zinc, cadmium, and then hang a left there to silver, kind of like this backwards L situation. And although these 3 here are transition metals, when they do form a charge, they actually do have fixed charges. Zinc and cadmium will both be +2, and silver will be +1. So pretty much those are the 3 transition metals that actually have fixed charges. Everybody else in the transition metal region, which roughly sketched is here, also down in this area as well, which again are not transition metals, but are still metals, like where we have lead, bismuth, and all those guys kind of right around here, tin. They have the ability to also make a variable type of charge. So kind of everybody in that greenish area, my badly drawn periodic table, has the ability there to really kind of make multiple types of positive charges. Also a reminder that, as we talked about, everybody on the periodic table does not have a charge when it is by themselves and uncombined. It is really only when kind of like the metal and non-metals get together, that's where we're going to get those transfer of electrons, and that's when they're going to actually make charges. Any questions on that there? So when we talk about naming, there are certain things that we really don't use sort of the formal name for, and you should use more of the common name for it. Here's a couple of examples of that. And really, I would say probably these 3 are the ones that you should know. H2O is water, and that's the name that you should use for it. It is not a trick question. Yeah, it is not trying to trick you. You should put water and move on with your life there on the quiz or exam, I suppose. It is not dihydrogen monoxide, because nobody wants a refreshing glass of dihydrogen monoxide. It doesn't sound refreshing at all, even though that is kind of maybe the formal name there of water. So you do not want that. This is NH3, which is ammonia. Ammonia is a weak base. CH4, which we will see again when we get into organic, that is the simplest organic compound you could have, 1 carbon, 4 hydrogens. It is pretty much what comes out of the gas vent there when you light a Bunsen burner. And I would say, oddly, even though this is table salt, most people still refer to it by its formal name of sodium chloride, sodium NaCl, and then we have some table sugar there. So I would say for us, you definitely should roll with the common names for those 3. When we come across it. So let's talk about naming compounds. And as I mentioned before, we have our 2 types of compounds. We have our ionic compound, which again is our metal and nonmetal. And that is going to create our opposite attraction there to hold it together. We have our 2 nonmetals, which is our covalent bonding. And again, that is where we have our sharing of electrons. Now, when we look at ionic compounds, there are a couple of things that we want to think about when we kind of do an ionic compound and kind of put it together sort of correctly. But before we do that, let's talk about two types of ionic compounds, and that is type 1 and type 2. They are binary compounds, which just basically means they have two elements involved. They contain a positive cation and a negative anion. When you name these guys, it is always the positive guy first, followed by the negative. And when you write the formula for that, it is also always positive first, followed by the negative. Now, speaking of formulas for ionic compounds, they actually do not have an overall charge when you write the actual formula for an ionic compound, even though they are basically two things that have charges. So what I mean by that is when we take something that is a positive ion, let's just say we take calcium, and we want to put it together with something like bromine. And calcium is group number 2, so it has a +2 charge. Bromine is group number 7, which means it has a -1 charge. When you want to put these together, and obviously this guy over here is our cation. Over here would be our anion. When we go to put these guys together, we want to put it together in the simplest way possible that will essentially yield us a 0 for the charge. So when we add up all the positive charge there and all the negative charge, it needs to equal 0. You could do that multiple ways, but you just think about like a math problem if you want. You could actually just multiply the two numbers together. That's 2 and 1, which is 2 is the common number there between them. So in this case, we actually would need more of the minus guys, right? And this will give us our proper formula. Once you balance it out, this is -2 overall, and that balances out the +2, right? So -2 and +2 gives you 0. And at that point, you can just count what you got. I got 1 of those calciums, and I got 1 and 2 of those guys. And we would write our formula like so, CaBr2. When we write the subscripts and nothing is written like here, it always, by the way, goes to the guy to the left, and that is assumed to be 1, but we do not usually use 1 for anything in chemistry. So if you don't see a number next to an element, it basically means you have 1 of them. The 2 here goes to the Br. So the proper formula here would be CaBr2. This again is the formula for this guy. It has absolutely no charge, but it is actually in reality made up of things that do have charges. So when you write your formula, putting your positive guy and negative guy together, you need to balance it in the simplest way to 0. And remember that although we don't have a charge when we put them together, they are still things that do carry charges. Questions on that? Yeah. There is a reason for that, and we'll actually hit it when we talk about bonding, hopefully today. But in this chapter, when we hit to the bonding part, we'll talk about why that really is and why, for example, we need 2 of them versus, we just need 1 of those other guys. Other questions? Okay. So again, if I had something like obviously sodium, which is group 1, and chlorine, which is group 2, or chloride, chloride obviously being group 7 with a -1. When we put this together, we have a +1, -1. We again just need basically 1 of each of these to get us to 0. I would highly recommend that you think about doing it this way, kind of like a math problem and figuring out the balancing charge. Sometimes people are taught, I won't say sometimes, a lot of times people are taught just to do this move, like take the charges you got on top and move them down to the bottom as the subscripts, and vice versa. Like move this way, move that charge, that number that way to get the charges. And it does work like 93% of the time. So if you're good with 93% of the time at working, blindly just kind of randomly doing it without thinking, you'll be okay. But it does not work all of the time. So sometimes it's better just to kind of think about, balancing out the charge. And if it helps you to visually think about it, you can obviously write it out there and you could just balance out the charge. And like I just did there, all you have to do again is just count how many of each of those you got and put them together correctly. So again, I would say people are oftentimes taught that way, just kind of move those things up and down without really thinking about it, and you will get wrong answers sometimes, but it will work 90 some odd percent of the time. So I guess that's sort of good, I suppose. We just want to blindly do that. Any questions on that? Yeah. So speaking of these guys, as I mentioned before, there are two types of ionic compounds. So when we talk about type 1 and type 2, we are talking about an ionic compound, which is our metal and non-metal. Type 1 compounds versus type 2 compounds, it all is really based on the actual metal is the difference between them. So when you have a type 1 compound, pretty much the metal has a fixed positive charge for the metal. And as I mentioned at the beginning there, that's going to be basically your group 1, your group 2, your group 3, your silver, your zinc, and your cadmium. So these are the guys here on the periodic table, metal-wise, that have a fixed positive charge. The difference between type 1 and type 2 is they're, again, still both ionic compounds. The difference, again, is the metal. So in a type 2, it is a variable positive charge on the metal. So basically, that is going to be your transition metals. And just to the right of those, under the staircase. So what I mean by that is obviously here, the transition metals are in the middle. But just to the right of transition metals, underneath the staircase, where I kind of pointed out earlier, where we have lead, tin, bismuth, all those guys over here, they're technically not transition metals, but they also have pretty much the same sort of ability of creating variable type of positive charges. So they're kind of grouped together in terms of the naming aspect of it as a type 2 sort of compound. Any questions on that? So as an example there, you can see chromium, it could be +2 or +3, depending on the situation, and copper +1, +2, depending on the situation. So let's talk then about ions. And let's just say we wanted to name just the ions by themselves. So not the ionic compound together, just the individual cation or anion. So if you are given the formula for a cation, which is a positively charged ion, like H+, like Li+, like Ca2+. These are all formulas for cations. Because they are ions, when you write the formula for this, the cation by itself, they do need to have a charge on them. So that's why they all actually have the charge written. So they're not combined at this point. We're just looking at the ion by itself. You do need to write the charge in when you write the formula for it. The good news is for cations, we simply just use the whole name of the element. So to name those guys, this guy would be the hydrogen ion. This would be the lithium ion. This would be the calcium ion. So anybody that is a positively charged ion, you essentially will use the whole name of the metal. Most of them are metal. Hydrogen is the only one that's really not a metal in this case. It's actually still a non-metal. When you do the non-metals, though, and they make anions, like H-, Cl-, O2-. Once again, these are all formulas of anions, and because they are ions, we again need to include the charge when we write the formulas for each of them. What we do with the negative anions is we really we keep the first part of the name, if you will, or part of the name. We drop the last part of the non-metal name, and then we insert IDE at the end of it. So sometimes it's a little bit more than the last part of the name is dropped, but somewhere towards the last part, middle to last part of the element name, we drop and we add IDE. So hydrogen ion becomes now negative, which is now known as the hydride, IDE ion. Chlorine becomes the chloride, IDE ion. And oxygen, which takes out a lot of the name, becomes the oxide ion. So we take a little bit more out of oxygen there in terms of the name. So negatively, guys, here that are ions that are nonmetals will get IDE at the end of the name. Positive guys that are cations will just use really the whole name of the element. There will be some other additional things we will add as we go through it. You also might notice that our friend hydrogen is on both sides here. Yeah, it is one of the only elements that can go both ways. It can be positive or negative depending on the situation. I would say probably a majority of the time, hydrogen will be positive. It will be negative if it comes after a metal. So if it comes kind of bonded after a metal, like for example, if you had LiH, that is lithium hydride, and the lithium is actually the cation with a positive charge, and the hydrogen actually has a negative charge in that case. This is also why when we do the formula here, -1 + 1 = 0. We just need one of each of them to put them together properly in the formula. Any questions on that? So if you're asked to write the formula for either a cation or an anion, you need to make sure that you do include the charges. And obviously, if you have to name them, whole name for the positive guy, IDE at the end for the negative guy. Again, when you put those two together, no charge on the formula. So that's an important thing. Distinction. If you put the metal and the non-metal together with their ions, you need to get it to 0 in the simplest way possible. Any questions? Okay. All right, so let's talk about type 1 ionic compounds and really how we go about naming them together. We kind of just did it essentially. When you have a type 1 compound, which again is our fixed positive charge on the metal, it is also a metal and a non-metal together. And by the way, when you are naming anything that a metal and non-metal are together, or a metal is involved, the metal is always the most important thing in terms of how you go about naming it. So the metal really is the most important thing in terms of how you should name it. And again, that metal is going to be from group 1, 2, 3. It will be silver, zinc, or cadmium, maybe. And when we have this situation, all you have to do if you have the formula is you take the whole name of the metal, and for our non-metal, you just roll with the IDE ending of it. So that's it. No more. Don't overthink it. You have the formula. Identify it as a metal, non-metal. Identify it as a type 1 metal. And all you have to do at that point is just roll with the whole name of the metal, the IDE part of it. So as we saw there a second ago, we had our calcium and we had our bromine or bromide. When we put it together, as we talked about, we again need an extra one of those guys, and that's going to give us CaBr2. And here, what we would want to look at if we were given this formula to start with is I would look at this guy and go, that's calcium, that's a metal. I would look at this guy and go, that's bromine, that's a non-metal. That should tell you it's ionic. And then I want to look at the metal and I go, calcium is in group number 2 on the periodic table. That means it has a fixed charge. That tells you it's a type 1 compound. Yeah. At that point, you just roll right into this and you use the whole name there of the metal, which would be calcium. And then we go with bromide, IDE. Now, let me answer the question as you're going to ask right now. No prefix, yes? The 2 doesn't matter at all, yeah, in terms of naming here. You should not use a prefix. Was somebody going to ask that? Maybe. Usually somebody asks that. Shouldn't it be like dibromide because there's like 2 of them? And the answer is no, unless you want an X, yes? So don't do that. There is a time and place for prefixes. And if you have a metal involved, that is never the time nor the place to use a prefix. So you should not use a prefix here. It doesn't matter if you have 30 of the BRs at the end there. It doesn't matter if you have 20 of the calciums to start with. You just roll with whole name for the metal. Non-metal gets the IDE. There is no place for prefixes in this type of naming. So that is a very, very common mistake that people make. I think they think it's more chemistry-like if you lay up some prefixes on things. You know, it sounds more scientific like that, put a little dye in there. So again, it doesn't matter. That's also why when we look at NaCl, again, if we were to sort of analyze this, that is a metal, that is a non-metal. Once again, that tells us it's ionic. We're going to look at the metal, which is sodium from group 1. That means it has a fixed positive charge. That tells me it's type 1. That tells me I'm done thinking. I'm just going to roll with how I should name it. And again, we're going to use our whole name here of our metal. And our non-metal, once again, will get the IDE treatment. So we'll get our sodium chloride. Any questions on that there? All right. So when we do see the formula, as we talked about, it should not have a charge. But once again, when you do see a formula for an ionic compound, you should understand that it is made up, again, of two things that do have charges. So here with our Ki, once again, if we were to look at that, that's a metal potassium. I is a non-metal. That tells me it's ionic. Metal, always the most important one in this situation when it's involved. And K is in group 1, which tells me it has a fixed positive 1 charge, tells me it's a type 1 compound. At that point, that is all the information I need to name this. I'm going to go, obviously, like it says down there, potassium, whole name of the metal, and we're going to put the IDE there at the back end there of the iodine, and it becomes iodide. Once again, this is no charge on the compound when they are put together, but if you were asked to write the formula for the cation and the anion, which are the ions, you would write K plus for the cation, would be the formula for the cation, and you should write I minus for our anion. And this, once again, is why we only need one of each of those, because plus 1 and minus 1 equals 0 in this case. Any questions on up there? All right. Well, why don't you try some, perhaps not the second one, because clearly I just did that one 4 times. So let me try to get rid of that one. Let me put some on here. Why don't we do something different? Let's do Li3N. Why don't you also give the formulas for these names, because you got to go both ways here. So why don't you try this? We'll use calcium. Let's use calcium oxide. Why don't you give the formula for aluminum sulfide? And why don't you do magnesium? We'll do bromide. All right. So we're looking for proper names on the left there and proper formulas on the right. Take a few moments, see what you come up with. Okay, so let's take a look, see how you're doing. So we'll start here on the left. So once again, if you're given the formula, really probably the best thing to do is to try to think about what things you got going on, and that will help you with the naming part of it. So here again, we have K, which is a metal. We have Cl, which is a non-metal. So again, you got the metal, non-metal. So automatically that should hopefully signal to you that is ionic compound happening. Once again, as we talked about, whenever a metal is involved, is always the most important thing. So we want to look at to where that potassium is located on the periodic table. And we should hopefully see that it's on group 1, which tells us it's a fixed positive charge of plus 1 in this case. So that tells you that we are dealing with a type 1 compound, right? So those are things we want to work through. Once you kind of get it at that point, we know all we have to do when we have a type 1 compound and we need to name it is use the whole name of the metal, which in this case should be potassium. And all we have to do for our nonmetal again is drop the last part of the name and add that IDE, right, to our nonmetal at the last part. And we will make that chloride in this case. Any questions on that one? Coming to the next one, again, we'll use our same sort of reasoning. We got Li, which is a metal. We got N, which is a nonmetal. So again, that tells me it is ionic. Once again, it is that metal that's most important. And lithium is also found in group 1, which tells us it's a type 1 compound. It has that fixed positive charge. So that tells us it's a type 1 compound, I'm sorry. That means we could again go with the whole name of our metal, which would be lithium. And again, our nitrogen would become nitride here, IDE at the end. Just like the second one, it doesn't matter if there's more than one. Doesn't matter if there's more than one of the first one either when you're naming these type of compounds. So again, no prefixes, even though you might want to try to do that, yeah? Why do we have 3 in that case? Well, if we look at really what each of these things are made up of, we go back to the first one, that means our cation in the first one is K+, right? And our anion here is Cl-, which is group 7. And again, that is why we have one of each of those. +1, -1 gives us just one of each of them in the formula. Here, though, our cation is Li+, right? And our anion is group 5, which has a -3. And that is, again, our cation here. That's our anion. And again, when we put this together, we need to get it to 0. So in this case, you could hopefully see 3 is the number we got to get to. So to get lithium to 3, I need 1, 2, and 3 of them basically to get it to +3 to balance out the -3 here. And at this point, all you have to do is count it, right? 1, 2, 3. That is why we have 3 there and only one of those, which is why we have 1 there. Question? It came from nitrogen, which is group number 5. So nonmetals, basically nitrogen and phosphorus for the most part, are going to be -3. So it's again +1, +2, +3, skip 4. And then at 5, you kind of go backwards, -3, -2, -1. Yeah. Other questions? Okay. All right. By the way, speaking of, if you were asked to write the formula of the cation, in this case of lithium, this again, what I wrote on the bottom is the correct one. This is not the correct formula. There is no such thing, yes? So when you're asked to write the formula for an ion, you should just take the one ion by itself and the appropriate charge that goes with it, not the subscripts and stuff like that. That 3 really means what we did down here. We have 3 of these individual Li pluses basically happening in this case, yeah? Other questions on that? Okay. So here, now that I scribbled all over it, we have Ba, which is a metal, and we have our friend hydrogen, which is actually a non-metal, right? So hydrogen is actually a non-metal. So again, that is ionic. Once again, it is the barium that's the most important thing. That is group number 2, which means it has a fixed positive charge of +2. That again checks the box for type 1. So we're ready to go at this point. We are going to go whole name of our metal, barium, and we're going to make this barium hydride in this case. And that is because the cation in this case, the positive guy, is barium from group 2, which means it has a +2. And then actually the anion in this case is actually hydrogen with a -1. And once again, when we put this together, +2, -1, we need one more of those guys to balance it out. And that is why the formula shows there are 2 hydrogens there, again, each at -1 to balance out the overall +2 charge of barium. Any questions on any of those there? All right, now that we have names and we want formulas, which you do need to be able to do, so how should we approach these? Well, we should really approach them kind of the same way. You want to really figure out what you got going on. So when I see calcium, I know that's a metal. Oxygen, which is oxide, is a nonmetal. So again, that's going to tell you it's ionic. In this case, we actually want to just think about the basic ions of each of those things, not putting it together or trying to do any of that first. We just want to figure out what the basic ions are. So calcium is group 2. So the basic cation that makes this up is calcium with a +2 charge. Oxygen is group number 6 on the periodic table, which means it's carrying a -2 charge in this case. Now that we have the basic 2 units, the positive guy and the negative guy, our next goal is to put this together, right, that the charge equals 0. So in this case, since I have +2 and -2, if I add that together, I get 0, which means just like I got here, I just need one of each of those, right? Again, keep it super simple. Don't overcomplicate. Yes. So all you have to do is think about it that way. Any questions on that there? Again, the combination of those two has no charge in the formula, but again, it is made up of 2 things that do have charges, which are ions. Now, aluminum sulfide. Again, we're going to do kind of the same idea. Aluminum is a metal. Sulfide is sulfur, which is a nonmetal. So again, that tells me it's ionic. So again, we just want the individual ions, and we're going to put it together correctly, hopefully. So aluminum is group 3, and it has a +3 charge. Sulfide is sulfur on the periodic table, which is group number 6. And again, we go 5 -3, 6 -2 -1. So again, 1, 2, 3, skip, 3, 2, 1, right? Positive to start, negative to end. Yeah. So that's going to be S with a -2 charge. Now, again, if you're not sure how to do this, just keep it simple, keep it visual. You can kind of see what's going on. If I take 3 times 2, what number do I get? You get 6, yeah? That is the common number we need for both of them, basically, to balance it out. So all we have to do is get aluminum to 6. It's already got 3, so 1 more will get me to 6. And to get the sulfur to 6, I need not 1, not 2, but I need 3 of them, right? So that is -2, -4, -6 overall. That is +3 and +6 overall. +6 -6 equals 0, right? When we add it together. At this point, what should you do? Just count what you drew, right? So that's 1 and 2 aluminums. I'll write it here. 2 aluminums, right? Number goes to the guy to the left. And that is 1, 2, and 3 of those. And there you go, yeah? So that is the formula at that point. Any questions on that there? Yeah. Yeah, that's one way if you're not really sure, what number you need to get everybody to or to balance it out. If you're not really sure, you could always just multiply the 2 numbers together, and that usually will give you the number you need to get each one to. That will give it 0 in the simplest form. So in this case, obviously, we had 3 and 2, which is 6. The top case, you don't really need that. Hopefully you can see that it's the same. But for example, if we looked at like the barium and the H- on the left there, 2 times 1 is 2, so we need to get each one to 2. So in most cases, you could, yeah. So the idea is, and when we get to the bonding part, really why that is, the idea is we want to combine these guys in the simplest way possible to get it to 0. What it actually will do, as we'll talk about, is it allows everybody to basically be really stable when they come together. So it allows them to create a really, really stable bond by doing that, basically. Yeah. Other questions? Okay, then we'll do the same thing here. Magnesium, which I know is a metal, and bromine, which is bromide there, is a nonmetal. So again, that's going to tell me it's ionic. Once again, magnesium is group number 2, Mg, which means it should have a +2 charge. Bromine, which is where bromide comes from, is group number 7 over here, underneath chlorine. Has a -1 charge, again, because it's group 7. Once again, we just want to put this together to equal 0. So hopefully you can see you really just need 1 more of those guys, right? So that's going to give you a -2 to balance out the +2 that's happening here. And at that point, we basically have 1 magnesium and 1 and 2 of the BRs. And again, that would give us our proper formula in this case. Any questions on that? So again, you obviously don't need to write out all the ions like I'm doing here. If it helps you, you should definitely do it. What's the difference? It doesn't really matter. But if it helps you to kind of visually see what you need to put together and how many of each, it's sometimes a good idea. Again, like I said before, you could just, without thinking, just bring these numbers down. And in this case, you'd be okay. But again, there will be several cases where you will not be okay if you kind of just do that without thinking about it. Okay. Questions? Yeah. Yeah. So there are, as we talked about at the very beginning, there are certain elements that have fixed positive charges. So no matter what happens, they're never going to make any other charge than what they make. And those are, starting over here, group 1 will be +1 because they're metal, so they'll lose electrons, become positively charged. Group 2 will be +2 because they again lose metal, so they'll be +2. Really, group 3 is aluminum, and that'll be +3. At that point, you should skip 4, and now going backwards, the non-metals up on top, which will be negative because they're going to gain electrons. -3 for 5, -2 for 6, and -1 for 7. The 3 exceptions for the transition metal region: zinc and cadmium +2, hang a left, silver +1. Yeah. Yes. I'm sorry, I can't hear you. The noble gases? We can name them, but there's a different way that we name them. So they are typically, in most cases, chemically inert, which means they don't react. So they don't technically end up in a lot of things. So in this type of naming, you probably wouldn't find like a metal and a noble gas coming together because they're pretty much happy the way they are. So they're not going to usually come together and stuff like that. Yeah. Other questions? Yeah. You mean the one on Monday, or? Yeah, of course. No, I'm kidding. I'm kidding. I'm kidding. Kidding. Don't send me the emails. I'm just kidding. All right. It's all right. No, this is exam 2 stuff. Yeah. All right. Let's continue on there. There's type 1. All right. Now let's talk about type 2 compounds. Now, type 2 compounds are also ionic, which means they also are metals and nonmetals. So these guys, again, are also ionic, also metals and nonmetals. And the deal here with these types of compounds, if I could spit that out, these types of compounds, is very similar to type 1. The metal, again, is the most important thing. So the take-home message is, if you're naming something, you have a metal, that's pretty much where you should start. You should start looking at the metal. It's going to help you determine how you should name these things. So the difference between a type 1 metal and a type 2 metal is, a type 2 metal is basically going to be your transition metals, are just to the right, as I was talking about on the periodic table. And again, that is this region over here where we see lead, Pb, Sn for tin, and bismuth, and that sort of area, antimony as well. Even though, they're not transition metals, they're sort of named the same way, so they kind of fall in with them. What they have in common is, again, they are the ones with the variable positive charge. So the good news on how we go about naming these is, we essentially do the exact same naming as we do for type 1. So we still use the whole name of the metal. We still do the non-metal name there, where we drop the last part and put IDE. But the additional thing that you have to do when you're doing one of these type 2 compounds is, you have to actually include some Roman numerals. And the Roman numerals indicate the positive charge on the metal. So if you took one of those metals out by itself, just like one of them, not like the total charge, just one metal, what the positive charge is. So it is the positive charge on one of the metals, basically. So, and I mean that because it is a very common mistake that people make when they go to use the Roman numerals, is if they think it means how many of the metals that you have. So it is not meaning how many you have. It is, again, like I said, if you just took one of those metals by itself, whatever the positive charge is on it is what the Roman numeral will be. So what that means is you need to, in these cases, figure out what the charge is on that metal. The other good news is you will always know the charge on whatever it's bound to. So whatever that metal is actually bound to in these type of compounds, you will actually know what the charge of that element is. And you'll be able to kind of work your way backwards and figure out the charge of it. So for example, the one I think that was on the page there, FeCl3. Now, in this case, we want to still do the same thing. I see Fe, which is iron, which is a metal. I see Cl, which is chlorine, which is a non-metal. And again, that tells me it's ionic. Once again, when a metal's involved, that is who we want to look at. And when I look at my metal, I find them dead center almost on the periodic table, right there. And in that region of the periodic table, that is the transition metal region, right? And that is the key thing that should trigger you to say it probably makes a variable type of charge. So if you have somebody in that transition metal region, except these guys, but if you have somebody else in the transition metal region, R to the right, that is how you know that this is a type 2 metal. Now that we know it's a type 2 metal, we need to figure out what is going on with the charge. Again, I like pictures so you can visually see what's going on. So what we know at this point is I have an iron ion hitting there, but I'm not really sure what the charge is. But I do know that if I go to the periodic table and find Cl, what type of charge should Cl have? It is group number 7, which means it should have what charge? -1, yeah? So I should have a Cl with a -1. But in my formula, do I have just one of those? I have how many? I have 3 of them. So 1, 2, and 3. Now, if I add up all of that negative charge, what's my overall negative charge for all 3 of those? It is a -3. Remember that we want our positive and negative to balance, right? So what does my positive guy has to be in this case? It has to be a +3 to get me to 0, right? There it is, right? I just figured out what the charge is. So you will always know what the charge is, like I said, of whatever it's bound to. You can then work your way backward. Now that I have everything that I need, I'm still going to follow my rules here. I'm still going to use the whole name of the metal, which would be iron. I'm going to use a Roman numeral once again to indicate not how many I have of iron, but the actual charge. So the actual charge number is 3. 1, 2, 3. The actual charge. Once again here, just like in type 1, it does not matter how many of those Cl's I have. I'm still just going to call it chloride. And that's a little iron 3 chloride for the evening tonight. Yes. Any questions on that one there? So that is how you want to approach it. Why do we need a Roman numeral for these type of guys? The reason is, for example, let's just say I had this guy. Let's just say I had FeCl2. What would this name be? Let's do the same thing. I got iron, which is a transition metal, so I know I need to figure it out. I know Cl, as we saw below, is -1. And how many do I have in this case, though? I only have 2 of them. That gives me a grand total of negative charge in this case of, which means my positive charge is +2 in this case. So that means that this name would be iron Roman numeral 2 for the charge. and again, chloride. Basically, naming is telling everybody, hey, in the first case, I'm doing the iron with a +3. In this case, I'm talking about iron that has a +2 charge. So that is why we need the Roman numerals, because iron can have a variable charge, and we want to know which one we're dealing with, right? We don't need those Roman numerals for something like sodium, because no matter who you hook up sodium with, it's +1 all day, yeah? And calcium, same thing, it's +2 all day, and that's like known. Same thing with this guy, it's +2 all day, +2 all day, and +1 all day. It doesn't really matter. And that's why we don't need the Roman numerals on those guys, because it's implied by the element that that's the only charge it can make. But if you have something in the transition metal region, it can make multiple types of charges, so you have to include it. Question on that. By the way, if you did have just the ion by itself, you would also include the Roman numeral. This would be the iron 2 ion. Yeah. So just kind of like what we did with the positive guys, you would, if it's one of those variable charges, include the Roman numeral. Again, we don't need to do that on the ones we saw previously, because it was like sodium, barium, and all those guys that had, fixed positive charges. Question on that there. All right. So let's take a look at one here. So give the name of this guy. PB is lead, by the way. It's right about there on the periodic table. All right, let's take a look and see. Again, we will analyze it here. PB, which is lead, is a metal. Oxygen, which is O, is a nonmetal. So again, we know it's ionic. Once again, when a metal is involved, we want to look at the metal to decide how to do it. Location of the metal, number 82 there on the periodic table, is to the right of the transition metal, but underneath the staircase. So it falls as a type 2 because it can have multiple types of charges. So that tells us it's a type 2. So with that being said, I know I want to figure out what that is. I do know for sure that oxygen is group number 6, right? And what type of charge does group 6 have? Does have a -2, right? And how many oxygens do I have in this compound, by the way? You have 2. That's a grand total of, dare I say, 4. And that means that this guy is actually +4 in this case. And that would be a lead Roman numeral 4 because of the charge. And again, no prefix, oxide in this case, yeah. This would be a prime example of what I was talking about earlier, that if you just did this without thinking, you would end up with lead 2, which would be incorrect in this case, yeah? So again, does not work in all situations. 93% of the time, you'd probably be all right. But, 7% not so all right. Yeah, so there's a lot of situations where just kind of doing that switcheroo will not give you the right answer. Do you have a question? That would be the correct name, yes. Yep. So again, like I said before, people will oftentimes just kind of do that switcheroo, and they will end up with something like this as lead 2 oxide, which is incorrect. And again, that's why sometimes, the visual pictures is a good thing, and just kind of visually see what's going on. Question on that. Any questions so far? All right. We are kind of in the middle here of group 2, so let's continue talking about them. Now, as I scratched it out there, let me erase my stuff on that page. There is really an older system that's used sometimes to name these guys that have Roman numerals. We will not be using it, but sometimes, for example, you may see something like ferric chloride or ferrous chloride, and it's more of like the old school sort of name for the elements, and they use ic or us instead of Roman numerals. The ic is the one that has the higher positive charge. The OUS is the one that has actually the lower positive charge. We will not use those in this class. We will strictly use for type 2 Roman numerals. but occasionally, especially for copper and iron, sometimes they still pop up a lot. Even till today, people still use like cupric, cuprous, ferric, and ferrous. But again, we won't be using that in this class. So here are some examples of some of our type 2 elements. And again, you can see they all have Roman numerals. One of the weirdest ones for most people, or the hardest one sometimes, is mercury. And mercury is over here. And mercury like this with all the 2's, and mercury like this with just 1 2. Oddly, the one that has the most 2's is actually mercury Roman numeral 1, while the one with only 1 2 is actually Roman numeral 2 there for mercury. It is a good question. The question is, why is it that? And the answer is mercury 1 actually comes as what's referred to as a dimer. There are actually 2 plus 1s stuck together, which is why there is an overall charge of +2, and also because there's 1 and 2 of them, why there's the 2 on the bottom. So that's the reason why. So that's also how you know it's like mercury 1, because that 2 tends to stick around. So for example, if you had Hg2O versus HgO, this is actually mercury 1 oxide because there's that extra 2. This is actually mercury 2 oxide because there's no 2 there. So that extra 2 kind of sticks around, and that's how you kind of know, it's mercury 1 versus mercury 2, and it kind of comes together with something. So, and again, you can still do the same thing as we did before. You would go, okay, I'm not really sure, but this is -2, so that is +2. Here, though, you would have to kind of realize that you got 2 of those guys, yeah? So you got to think about that each one has to be really +1 in this case to get you to +2. So again, I would say most of the time that 2 on the bottom kind of hangs out, and that's how you kind of know that it is that. All right, we talked about sort of the rules here. Again, same thing as type 1. You do need to do the addition of the Roman numeral. And you, again, should always know what it's attached to, and you can work your way backwards to get the charge on the metal. So why don't we try some here? So for each of these, give the proper names. And let me give you some names and give some formulas. Let's do iron 2 nitride. Let's do copper 1 oxide. And let's do SnO2. By the way, Sn is 10. That's something that you should know at some points, yes. Actually, I just gave the formula, huh? No, I wasn't meant to do that. I was supposed to give you a name. That's all right. Give the name for that one as well. Why not? We'll do a bonus one there. Like, what doesn't look the same as all the others there on that side? I think it's the bottom one. All right, let's give a right one here, maybe. Let's go with let's go nickel 4 chloride. We'll do that one on top. All right. There you go. Okay, so let's see how you're doing on these. We'll start on the left here. So we're gonna go over names. Again, identifying what we got going on. Cu is cobalt, which is a metal. Cl is a non-metal. So once again, that tells us it's ionic. And as we've been talking about, whenever we have a metal involved, that's the one we want to look at. So again, cobalt's going to be found here in the transition metal right next to 27-ish there. So that means it has a variable charge. So again, we now know it's going to be a type 2 situation. We do have to do a little extra work, right? We got to kind of figure out the charge on it. So here we may not know the charge, but we should know the charge on the Cl, which is group 7. That means that it should have a -1. And once again, we have 3 of them, which is going to net us a -3 charge. So once again, here to balance it out, our cobalt needs to be +3 in this case. That would give us whole name of the metal, cobalt. Now we do need the Roman numeral, which again is not how many we have, but the actual charge. So we got 3. And again, here in this type of situation, because of metals involved, no prefixes, so just chloride at the end. Question on that one there. Looking at the next one, Cu is copper, metal. I is iodide, non-metal. So again, checks the ionic box. Copper also in the periodic table 29. I hope it hasn't moved, so it should be there. That is type 2 because it could have a variable charge. Again, we're going to do the same thing. I know I got 1 copper, and in this case, I have 1 I, which is group 7, should have a -1 charge. And that would tell me that my copper here should actually have a +1 charge in this case. And again, we would have copper Roman numeral 1 for the charge and iodide. Question on that one there. Sn is tin, which is a metal. Again, it's actually over here to the right of the transition metal regions underneath the staircase. Br is a non-metal, so again, that checks the ionic box. Tin, as I just described, is not a transition metal, but one of those ones to the right that basically behaves the same way. That means it can have a variable charge, so again, that checks the type 2 box. Once again, just drawing it out, maybe to make it simpler, we got Br, which is group 7, has a -1 charge. There are 4 of them. So again, if it helps you, just draw them all out, yeah? So and then count 1, 2, 3, and 4. That's a -4. That means since we only have one of these, we need a +4 happening on that guy. And that would get us 10 Roman numeral 4. And again, bromide doesn't matter how many we got going on there. Any questions on those there? Since I messed up and did that guy on the bottom, we'll do that one too, since we're naming here. Once again, that's still tin, and that is oxygen, which is a non-metal, checking our ionic box. Here again, tin having variable charge. So I know tin will have that. Oxygen here is group 6, which means it should have a -2 charge. And here we do have 2 of them. So that is going to get me a -4. There we go again, a situation where it will not work, right? The crossover move. That is going to give us a +4 for 10 in this case. And that is going to be 10 Roman numeral 4 because of the charge. And this would be oxide. Any questions on any of those names, where any of that stuff came from? All right, then we got names and we want to do formulas. The good thing about this is it says nickel Roman numeral 4, which means what charge does the nickel have? It has a +4 charge. That's what the Roman numeral means. So you don't even have to figure out anything on that. It basically tells you what it is. The chloride is group 7, which means it has a -1 charge. Again, we need to get to 0, right? So we do need 4 of the Cl's there total to do that. And if you draw it out, it looks something like that. -4 +4 gives us, if we just count, I need 1 nickel and 1, 2, 3, 4 of those guys. Looks something like that, yeah? Any questions on that? Iron Roman numeral 2 means iron has +2 charge, that's it's a metal. Nitride is nitrogen, which is obviously group number 5. That is a -3. In this case, again, the common number between 2 and 3 is 6, right? So that is the goal, to get everybody to 6. So to get nitrogen to 6, I just need 1 more, total of 2. For iron, we actually need a total of 3 of them. That's going to give me a +6 overall and a -6, which when we add them together gives us 0. To get the proper formula, I got 1, 2, 3 irons. So Fe with a 3 next to it, and 1 and 2 nitrogens, and then a 2, right? There we go in that case. Yeah. Any questions on that there? Copper Roman numeral 1 means copper will have a +1 charge. Oxygen is group number 6, which has a -2 charge. In this case, you hopefully could just visually see that perhaps we just need one more copper to go over there to balance it out. And that would give me 1 copper, 2 coppers, and 1 oxygen basically there. In that case, yeah. Any questions on them? Again, if it helps you to draw out the kind of ions like I'm doing, I would recommend doing it. Yeah, and then you can just cancel it. You obviously, again, don't need to draw out the ions like I'm doing, but if it helps you, do it. Yeah. Any questions on type 2 guys there? All right. Well, type 1, type 2. Feel like type 3 has got to be coming soon. All right. So as we've been talking, when we have our metal, non-metals, again, there are certain ones that do not need Roman numerals, as we talked about, because they have those fixed positive charges. And again, those are everybody from group 1, group 2, and group 3 on the periodic table, and our zinc, cadmium, and silver. And again, pretty much everybody outside of that will need Roman numerals because of their ability basically to make a variable type of charge. All right, good naming. I think we did that. Here's a little decision tree to kind of help you decide which way you should go. Again, really it's that metal that you want to look at as to whether or not you need the Roman numeral or not. All right, type 3, I felt it coming here. And this is the place, the time that you've been waiting for. You should go free and have fun with prefixes here. Yes, this is the place that you should use prefixes. So prefixes are actually used here with type 3. Type 3 is actually a different type of compound. It's a covalently bonded compound, sometimes referred to as a molecular compound. It is a compound that's actually sharing electrons, and it's usually between 2 nonmetals. So again, everything that we've been talking about with type 1 and type 2, those are again ionic compounds, and they are again involving ions. These are non-bonding guys that are going to be sharing electrons, are a non-metal that will be sharing electrons, and there are no ions involved. The good news is type 3 is like the simplest ones to name. The bad news is they're also the ones that people screw up on the most because they don't think it's that easy. So it actually is probably the simplest ones that you could name, and probably even the simplest ones that you could write a formula for if you have a name. But again, sometimes people mess it up thinking it's got to be maybe more difficult than it is. So with type 3 compounds, it only contains nonmetals, and pretty much the way we name it is we actually will use a prefix, if necessary, on the first name, and we'll use the whole element name. And we will use a prefix on the second name, and we will do the second name like we've been doing. We'll kind of take the non-metal part, and we'll put the IDE at the end. So we kind of go prefix, if needed, on the first name, and prefix on the second name there, our element that's present. What are our prefixes? Well, we have mono, which is 1, right? We have di, which is 2. We have tri, which is 3. We have tetra, which is 4. We have penta, which is 5. We have hexa, which is 6. We got a little hepta, which is 7. Got a little octa, which is 8. Maybe a little nona, which is 9. And maybe a little deca, which is 10. Maybe I'm making it up. I don't know. That seems right, I think. So these are the prefixes that we use. And there are a few rules that we want to follow when we're doing this. And the first rule is pretty much this. We actually do not use mono in the first name. But it is okay in the second. Yeah, so we don't use mono in the first name, but we can definitely use it in the second name. Another very common thing that occurs is sometimes when you take the prefix and you put it in front of the element, you will end up with 2 vowels that come together, back-to-back vowels, basically. So, for example, you may end up with an O from the prefix and an O from the element name, or you may end up with an A for the prefix and a O from the element name. And typically speaking, we do get rid of that kind of vowel from the prefix when we do that. So for example, CO2, yes. C is carbon, which is a nonmetal. Oxygen is oxygen, which is a nonmetal, or O is oxygen, which is a nonmetal. That is two nonmetals. That checks the box of type 3. That also should check the box of you should be extremely happy because that's all you need. There is no balancing of charges. There's no like pluses, minuses. It's just like basically write what's there. So I have one carbon, right? Prefix for one is mono. Should I use it on the first name? No. So we just use the whole name. That's carbon. I have two oxygens. Prefix for two is di. And then the oxygen becomes oxide. So that is carbon dioxide. We're done. Yeah. So nothing to balance, no charges, nothing like that, right? Now, when we take CO, C is carbon, which is a nonmetal. O is still oxygen, which is a nonmetal. In this case, we still have one of the carbons, right? And that would be carbon, no prefix, because we don't use mono in the first name. We only have one of oxygen. Okay to use a prefix? It is on the second name. So if you just used a prefix like it is written, you would go monoxide with a double O action. Yes. Do we call it carbon monoxide? No, you get carbon monoxide poisoning. Yes. No, hopefully you don't get that, but you understand what I'm saying. But here we would want to, because we got the back-to-back oxygens there, we would want to drop the O off of that, and this should be carbon monoxide. Yeah. Again, nothing to balance, nothing to worry about. The way we do this is in the formula, first element goes first in the name, second one goes second in the name. So just the way it's written is how you do it. Questions on that there? All right, that's pretty much what I just said, I think. That is not the right table. So again, here again is a prettier table of what we just talked about, and we do sort of drop some of those vowels off of it. I would say probably a like A into an O with oxygen is where you're probably going to hit that the most. Oddly though, two I's in a row is okay. So you could go two I's in a row, it's usually okay. But an A and an O, you got to drop the A, or O and O together is usually the one that you need to drop. And again, we do drop the vowel from the prefix is where we take the vowel out of. There you go. Now, again, as we talked about before, we go common name on these guys. Yeah. So again, H2O, not a trick question, although I usually enjoy the answers I get on that one. Everything but water is written pretty much. But remember, it is water, and that's what you should use. Our methane is another one common name, and ammonia. So those three should always use the common names. You should not use nitrogen trihydride. You should not use dihydrogen monoxide, and you should not use carbon tetrahydride. Just doesn't even sound right, right? So don't use those names. Use the common names for those things. Go ask somebody for, again, a refreshing glass of dihydrogen monoxide and see what you get. I don't know. All right, so why don't you do the names here? Maybe not that name because, well, I just did that name, so maybe not that one. Let's do N2O5. And why don't you also write some formulas here? Let's do sulfur hexabromide. Let's do dioxygen. Just make up some stuff. Pentasulfide. That sounds fun. And I don't know. Let's do carbon. So again, you do need to be careful because people very commonly do make a lot of mistakes with these. So what we're looking at is type 3, and we got I, which is a nonmetal. We have O, which is a nonmetal. And again, that tells us it's type 3. And as was the question a second ago, this is basically sharing of electrons. So there are no ions involved. So we only have ions in ionic compounds like our type 1 and type 2 compounds. So there's really, like we talked about, really no balancing of anything that you need to do or worry about charges. So what we need to look at here is really just pick the right prefixes and follow the right way to name it. So obviously here I has 2, so the prefix for 2 is di. And again, we use the whole name there of the first element. And again, in this case, usually the 2 i's are okay. Here, this is 7. The prefix for 7 is hepta, right? And the second element does get the IDE treatment at the end. So this is going to be hept oxide. I dropped the A because we would then have a and O together here. So this would be one of those cases where we would want to get rid of the A in this case so we don't get that AO combination that occurs here. Question on that one there. Coming here, that is nitrogen, which is a nonmetal, oxygen, which is a nonmetal. Once again, that's happy thoughts there as we get a type 3, right? So again, nothing to balance. All we have to do is pick the right prefix. Once again, we do have 2 nitrogens, so the prefix for 2 is di. Again, whole name here of our first element. Second element going to get the IDE treatment, so that's going to be oxide. And we do have 5 of them, so the prefix for 5 is penta. Again, we're going to run into that AO situation there. So we're going to drop the A off of the prefix and just go with the O there from the oxygen. Question on that one there. PCl3, P is phosphorus, which is a nonmetal. Cl is chlorine, which is a nonmetal. And again, that tells us type 3. Once again, we have 1 phosphorus. Prefix for 1 is mono. Should I use it on the first name? I should not. So we're just going to use the whole name, which is phosphorus, spelled some way. And we have Cl, which will get the IDE at the end of it. And we have 3 of them. So the prefix for 3 is tri. So that's a little trichloride action happening there. That's a little phosphorus trichloride. Any questions on any of those names? So again, nice thing about these, like I've been saying, you don't have to balance, no charges, just simply pick the right prefix. Probably the quickest things that you should ever do is what you have on the right-hand side. And what we want to look at when we look at these guys on the right-hand side is I see a prefix. So that automatically tells me we know at this point, since I yelled at you 3 times, that the prefixes only go here, right? So it has to be a type 3 situation, right? So at that point, you don't have to do anything else other than write basically what it says. So I see sulfur with no prefix, which tells me how many do I have? I have 1, so I put an S. I see hexa, which is the prefix for 6. And I got bromide, which is Br, and I put a 6 next to it, and I'm done. Yeah. So like in a matter of like 2 seconds, you should pretty much knock through these things, right? So dioxygen pentoxide, pentasulfide. Again, we see some prefixes, which tells us, again, it's type 3. So di is how many? And oxygen is O. Yeah. So O2, right? Penta is 5. Sulfur is S. So you just need to put the numbers on the correct side, right? Which is always obviously to the right of the element. Is C with no prefix, means that we have 1 of them. And tetra is 4, which means we have 4 of those chlorides, and we get CCl4. Yeah. So a review of the 3 types of naming. Again, type 1 is ionic compounds, which again is fixed charge on the metal, and that is the important thing that you want to look at. So again, we go whole name, IDE on the last part of the name for the nonmetal. No need for a Roman numeral, as we've been talking about, since it does have a fixed positive charge. Type 2, again, also ionic, which means we have transfer of electrons and we have ions. Again, when we've been talking about metals are the most important thing. And that is the guys that have transition metals, which have variable positive charges. So remember, the additional thing that you need to do is use a Roman numeral, which does indicate the charge on the metal. Type 3 that we just did, again, that is the place where we do prefixes. And again, we just want to pick the proper prefix. There are no charges, there are no ions in these type of compounds, again, because they are sharing electrons. Any questions on those type of 3 naming? All right, the last type of naming we're going to talk about are compounds that contain polyatomic ions. And polyatomic ions are groupings of nonmetals together. So they're oddly type of compounds. They're odd things which are ions, but they are actually things that share electrons. So they are covalently bonded. They are actually sharing electrons. But the way that they share electrons, they actually end up with an overall charge, which actually makes them ions. So it's kind of an interesting thing in terms of what you got going on. So this is an example of a polyatomic ion, which is NH4NO3. We actually have two polyatomic ions in this particular compound here. And over here, this polyatomic ion is actually NH4 plus 1. It actually has 4 hydrogens and 1 nitrogen. That entire thing actually has a +1 charge. As I was mentioning a second ago, as we'll talk about when we talk about bonding, these guys are actually sharing electrons. And overall, because of the way they were sharing electrons and who they're sharing it with, it actually does end up with a charge. So we do treat them like ions, even though really internally they are covalently bonded and actually sharing electrons. This is nitrate over here, which is also a polyatomic ion. That 1 nitrogen and those 3 oxygens, they all stay as whole units here. And it has an overall charge of -1. Also, if you were to sort of draw what that looks like, they are sharing electrons. It looks something like this. And it has a -1 charge. And that is why when we put these two ions together, +1 and -1, we actually just need one of each. So it is actually still an ionic compound. And our goal with ionic compounds is to make sure that when we add them together, we do end up with 0 as the overall charge. And that is what we see here. We have one of these guys and one of these guys. So basically +1 and -1 when they come together will equal 0. Each of these polyatomic ions have a specific name. And this particular one here is what is known as the ammonium ion. Not to be confused with what we saw a second ago, which is NH3, which is ammonia. So ammonia is not a polyatomic ion. It is actually a compound. It has no charge, but NH4 plus is a polyatomic ion that does have a charge. So don't get those two confused. NO3 minus is nitrate ion. And the good news about sort of polyatomic ions is that much like what we did with type 1 and type 2, it really doesn't matter how many polyatomic ions you have in a particular formula. You actually just use the name of it. So you could have 3 of nitrates or 2 nitrates. It doesn't really matter. You just would call it nitrate. You could have 2 of the NH4 pluses. You would just call it ammonium. So it doesn't really matter what you have. So if we were to name this guy, we basically just put those names together, and that would be ammonium nitrate. So if you happen to have a compound that does contain 2 polyatomic ions, you basically just use the name of the polyatomic ions individually and put them together in the correct order. With that being said, probably what we see here, which is NH4 plus, is probably the only, one of the few, I won't say only, but it's one of the few positive polyatomic ions that you will come across, which means probably 99% of the time, you will basically come across a polyatomic ion that's hooked up with a metal. So you'll have a metal and a polyatomic ion, probably 99% of the time is what you're going to do. The good news about that is you basically will just default back to your type 1 or type 2. So most of the time you will probably have a metal, which is going to be your positive guy, and one of these polyatomic ions, which will be your negative guy. So for example, if we took Fe NO3 and we wanted to name this, we would kind of take the same approach. We see that we have a metal, and you will eventually know what this is, which is NO3 minus, which we just saw there, which is nitrate, which is our polyatomic ion. And basically, when you see this, and as we talked about before, whenever a metal is involved, that is the most important thing to look at, right? And that metal of iron is a type 1 or type 2 compound. It is a type 2, which means we do need a Roman numeral for it, right? And that's just like we did when we did our type 1. So we would do the same thing. You would take the iron and go, I'm not sure what it is. You would go, I have NO3 minus, which is nitrate. How many NO3 minuses do I have? I have 3 of them. And a reminder that, again, in each of these cases, those guys stay together because they are covalently bonded. That means overall charge, -1, -2, and -3, 1 for each of them. That would tell us in this case that the iron needs to have what type of charge? +3. And because it is a type 2, I do need my Roman numerals, and this would be iron Roman numeral 3. And again, does not matter how many of these you have, you just use the name of it, and it would be iron Roman numeral 3 nitrate. Now, if I had this guy, NaNO3, Na is sodium, which is a metal. That is still our nitrate, right? Sodium, though, which is the metal, is group number 1, which makes it what type of metal? It is a type 1. It has a fixed positive charge. That means I do not need Roman numerals here, just like we did previously. That means I should use the whole name of this guy, which is sodium. And this guy would be nitrate, which is the polyatomic ion name. Again, the formula is like that because sodium is +1 and the nitrate is still -1. Yeah, so we just need 1 of each of those. Yes, sir. You don't. So with polyatomic ions, we go straight with what the name of the polyatomic ion is, regardless of what it's bound to, regardless of how many you have. You just use the actual name of it. By the way, to finish up here today, why did I put parentheses here? And why did I not just write it like this? The last one I wrote implies how many oxygens do I have? 33, which is definitely not the case, right? So whenever you have more than one polyatomic ion, you do need to put parentheses around it and the number of how many you have to indicate how many you have. Otherwise, without the parentheses, you're actually doing something that you do not want to do in this particular case. Question on that there. All right, we'll lay it up there for today.